Welcome to the fifth session of Computational Fluid Dynamics with Mr. CFD. In this video, we will explore different types of discretization schemes that Fluent uses. In the Solutions section, under Methods tab, after selecting the pressure and velocity coupling method, you can choose different discretization schemes for each variable. Let's explain them one by one. The gradient of a given variable phi is used to discretize the convection and diffusion terms in the flow conservation equations. The gradients are computed in ANSYS Fluent according to the following methods: Green-Gauss cell-based, Green-Gauss node-based, Least Squares cell-based squaring. Each of these schemes calculates the gradient of different variables using its own methodology, and the choice between them depends on the accuracy required and the computational resources available. In the Green-Gauss cell-based method, the gradient of a variable phi at the cell C0 is calculated with the following formula. Nabla 5 is equal to 1 divided by v, summation of dot product of face 5 to face normal vector, where v is the volume of the cell and the summation is over all the cell faces. In a uniform grid, the value of phi at the face is obtained by calculating the average of the neighboring cell values. However, in non-uniform grids, it will be calculated as the weighted average of phi at neighboring cells based on the distance of the node to the center of the face. For example, consider a grid with cell values of phi as follows: 4 for the central cell, C0, 1 for the west cell, 9 for the east cell, 2 for the north cell, and 5 for the south cell. The values for other cells are 0.5, 3, 11, and 6. The gradient of phi at cell C0 would be calculated as phi w, would be the average of 1 and 4, which is 2.5, phi e is 6.5, phi n is 3, and phi s is 4.5. The normal vectors are I for the east face, minus I for the west face, j for the north face, and minus j for the south face. Therefore, the gradient nabla phi would be 1 divided by delta x, delta y, times 6.5 minus 2.5 in I direction plus 3 minus 4.5 in j direction. This results in a vector of the form 4i minus 1.5j divided by delta, reflecting the gradient of phi at cell C0. Assuming uniform grid spacing with equal delta x and delta y. In the gradient calculation using the Green-Gauss node-based method, the formulation for calculating the gradient at cell C0 is similar to the previous method, with the main difference being how the face value of phi is determined. Consider the same grid and values. In this method, the face value is computed by averaging the values of the nodes in contact with that face. In two-dimensional cases, each face usually has 2 nodes, whereas in 3-dimensional simulations, a face can have 3, 4, or even more nodes. The value at each face is calculated by averaging the node values of the adjacent face. The value at each node is determined by the weighted average of the surrounding cells that d is the distance of center of cell to node. If the grid is uniform, this process simplifies to the average of the neighboring cells, with m representing the cells surrounding the node. For example, in this uniform grid, the value of phi at a node is the average of the values 0.5, 1, 2, and 4, which equals 1.875. At another node, the value is 5.25, and at yet another is 7.25, with an additional node having a value of 3.25. The value of phi at the west face would be the average of its neighboring nodes, equaling 2.5625. The value of phi at the south face is 5.25, at the east face is 6.25, and at the north face is 3.5625. By substituting these values into the original equation, the gradient of phi at cell C0 is calculated to be 3.6875 in the I direction and minus 1.6875 in the J direction. This scheme reconstructs exact values of a linear function at a node from surrounding cell-centered values on arbitrary unstructured meshes by solving a constrained minimization problem, preserving a second-order spatial accuracy. The node-based gradient is known to be more accurate than the cell-based gradient, particularly on irregular, skewed, and distorted unstructured meshes. However, it is relatively more expensive to compute than the cell-based gradient scheme. The node-based gradient method is not available with polyhedral meshes. In the least squares cell-based method, the gradient of phi at the cell, C0, is determined by leveraging the concept that the gradient of this cell, dotted with the distance vector from the center of this cell to the neighboring cell, equals the difference in phi values between these two cells. Mathematically, this is expressed as nabla 5 dot product to distance vector Ri equals to 5 at cell Ci minus 5 at cell C0. The gradient vector nabla phi is unknown, but we can set up a system of equations based on this relationship that these unknowns are equal at all. Here, Ri represents the distance vector, decomposed into components along the grid directions, x and y directions in a 2D grid. The right-hand side is known and scalar. In 2D, the gradient nabla phi consists of components nabla phi I and nabla phi j. If we have, for instance, vectors r1 and r2 corresponding to distances from the cell, C0, to east and north neighboring cells, the system of equations is formed as follows. Ri1 and Rj1 times to nabla 5i and nabla 5j results delta phi 1. By completing the system of equations, we will have Ri2 and Rj2, Ri3 and Rj3, Ri4 and Rj4, delta phi 1, delta phi 2, delta phi 3, delta phi 4. This matrix is dependent only on the geometry. We have two unknowns, but there is 4 equations. The system of equations can be solved if there are exactly as many equations as unknowns. Since we typically have more neighbor cells than spatial dimensions, the equation system is overdetermined. There are more constraints than needed. The least squares method is used to find an optimal solution by minimizing the error. This is done by arranging the system in the form d nabla phi is equal to delta phi, where d is not a square matrix. The approach involves multiplying both sides by the transpose of d to obtain a square system. D transpose d is a square matrix, and we can multiply both sides of equation to inverse of it. The resulting system can then be solved by computing nabla phi is equal to inverse of d transpose d multiplied to d transpose delta phi. This factor is constant for stationary grids and only one time would calculate. This approach effectively minimizes the error in the approximation of the gradient by incorporating contributions from all neighboring cells, leading to a more accurate and robust estimate, particularly beneficial in non-uniform grids or complex geometries. For example, considering the same grid and values of 5 at these grid points, the matrix D for the system would be 0, minus 1. Multiplying the transpose of D with D yields 0, 2 and 2, 0. Calculating the inverse of this matrix, 0.5.50. The product of this inverse with the transpose of D gives -0.50.50 in the first row and 0.50 minus 0.5 in the second row. After substituting into the primary equation, the result for the change in values nabla phi would be, for instance, 400 minus 1.5. So the gradient is calculated as 4I and minus 1.5j. On irregular, skewed and distorted, unstructured meshes, the accuracy of the least squares gradient method is comparable to that of the node-based gradient, and both are much more superior compared to the cell-based gradient. However, it is less expensive to compute the least squares gradient than the node-based gradient. Now let's explain the discretization methods for pressure. Fluent provides us with 5 options to choose from. The first discretization method is the second-order scheme. In this scheme, the pressure at face F is determined by considering the pressure at cell I and adjusting it based on the pressure gradient across the cell. If we refer to the indices of the two cells adjacent to face F as I and I plus 1, the pressure at cell center I, written using a Taylor series expansion for the pressure at face F, is as follows. Pi is equal to Pf minus half delta x here. Delta x represents the distance between the cell center and face F, and it is defined as half of the length of each grid, times to first derivative of pressure with respect to x plus truncation error. The truncation error indicates the accuracy of the approximation associated with second-order terms. When working with non-uniform grids, the term partial derivative of pressure with respect to x multiplied by delta x divided by 2 can replace with the pressure gradient across the cell dot product to distance vector from the centroid to the face. By rearranging these terms, we can express the pressure at face F as P. F is equal to P, I plus nabla P, dot distance vector from cell centroid to face plus truncation error. The truncation error is neglected in order to simplify the calculations and assume ideal conditions for second-order accuracy. The second discretization method is the standard scheme. In this approach, the pressure at face F is equal to the weighted average of the pressures at the adjacent cells, based on the distance of the face from the centers of each cell. If we denote the adjacent cells with indices I and I plus 1, we define the distance from the center of cell I to face F as AI, and the distance from face F to the center of cell I plus 1 as AI plus 1. Using the Taylor series expansion for the pressure at cell I, Pi is equal to Pf minus A, I times to partial derivative of pressure with respect to x plus higher order terms. And similarly for cell I plus 1, Pi plus 1 is equal to Pf plus A, I plus 1, multiplied to partial derivative of pressure with respect to x plus higher order terms. To eliminate the derivative, we multiply the first equation by Ai plus 1 and the second one by Ai. Adding these two equations gives A, I plus 1 times to P, I plus A, I times to P, I plus 1 is equal to. These terms cancels out, and right-hand side will result as AI plus 1 plus AI times to PF. Solving for PF, we obtain this formulation. And by dividing the numerator and denominator by AI plus 1, the final form will result. This formula represents the discretizing operator for pressure with the standard scheme, where the pressure at the face F is effectively a linear interpolation based on distances from the adjacent cell centers. The PRESTO, pressure staggering options scheme, uses the discrete continuity balance for a staggered control volume about the face to compute the staggered pressure. This procedure is similar in spirit to the staggered grid schemes used with structured meshes. In this method, pressure value calculated and stores in the face rather than cells. Note that for triangular, tetrahedral, hybrid, and polyhedral meshes, comparable accuracy is obtained using a similar algorithm. The PRESTO scheme is available for all meshes. The linear scheme computes the face pressure as the average of the pressure values in the adjacent cells. In uniform grids, linear and standard schemes are same. Last one is body force weighted scheme. The body force weighted scheme computes the face pressure by assuming that the normal gradient of the difference between pressure and body forces is constant. This works well if the body forces are known a priori in the momentum equations, e.g., buoyancy and axisymmetric swirl calculations. Now let's explain the discretization methods for momentum. Fluent provides us with 4 options to choose from. The first discretization scheme is first-order upwind. In this scheme, the velocity value at the interface F is taken from the upstream cell. This means it is determined based on the conditions in the upstream direction. For example, if cell I is the upstream cell and face F is the interface with the direction of flow moving from cell I towards face F, we can approximate the velocity at face F using the value of velocity at cell I. Using a Taylor series expansion, we can express the velocity at face F as UF is equal to UI plus higher order terms. But in a first-order upwind scheme, we truncate the series by neglecting the higher order derivatives, resulting in UF equal to UI. The second scheme is a second-order upwind scheme, which we reviewed earlier. In this scheme, the velocity at face F is calculated using the value U at the upstream cell I plus the gradient of U dotted with the distance vector from the center of cell I to face F. The next scheme we can use for the discretization of momentum is QUIC, quadratic upwind interpolation for convective kinematics, which is a third-order scheme, also known as a higher-order scheme. In this scheme, the velocity at face F is computed as follows. UF is equal to 3/8 UI plus 6/8 UI minus 1 minus 1/8 UI minus 2, where I refers to the downstream cell, I minus 1 is the upstream cell, and I minus 2 is the second upstream cell. Using Taylor series to understand the approximation, we can write UI is equal to UF plus half delta x multiplied to first derivative of U with respect to x plus square delta x divided by 8 multiplied to second derivative of U with respect to x plus higher order terms. The distance from face F to the center of cell I is half delta x. The distance from face F to the center of cell I minus 1 is half delta x. The distance from face F to the center of cell I minus 2 is 3/2 delta x. By applying the Taylor series expansion for UI, UI minus 1, and UI minus 2, and substituting these expansions into the QUIC formula, UF is equal to 3/8 UI plus 6/8 UI minus 1 minus 1/8 UI minus 2, that by substituting Taylor series, The next term contributions of the Taylor series involving the first derivative cancel each other due to the specific coefficients in the quick scheme. Similarly, the second derivatives also cancel, resulting in UF. This cancellation of terms in the quick scheme results in a more accurate approximation of UF because it effectively accounts for potential curvature in the velocity profile across multiple cells, thus providing a third-order accurate solution. The scheme is more precise than lower-order upwind or central differencing methods. However, it's important to note that quick is generally implemented on structured grids, where the regular grid arrangement allows for straightforward computation of distance vectors and consistent application of the interpolation formula. The increased accuracy of quick comes with the added computational complexity and need for proper handling of boundary conditions and discontinuities in the flow field. In unstructural grids, quick scheme reduced to a second-order scheme. The last scheme is MUSCL. This third-order convection scheme was conceived from the original, monotone upstream-centered schemes for conservation laws by blending a central differencing scheme and second-order upwind scheme, as where phi CS is central scheme and phi SOU is computed using the second-order upwind scheme as described earlier. In this scheme, the right and left sides of a face can have different velocity values. This allows the scheme to handle discontinuities or phenomena such as shocks better. For the velocity on the left side of the face, UL, the formula is UL is equal to UI plus 1/6 of 5 UI minus UI minus 1 minus 2 UI plus 1 minus UI. Similarly, for the velocity on the right side of the face, UR, the formulation involves using values from three cells, I minus 1, and I plus 1. The exact formula might vary depending on the specific method being used, but typically it similarly uses linear or quadratic interpolations. In summary, to calculate the velocity at either the left or right side of the interface, the scheme utilizes velocity values from the three surrounding cells: the current cell, I, the previous cell, I minus 1, and the next cell, I plus 1. This multi-cell approach helps in capturing more accurate profiles across the face, especially in the presence of complex flow features. Unlike the quick scheme, which is applicable to structured hex meshes only, the MUSCL scheme is applicable to arbitrary meshes. Compared to the second-order upwind scheme, the third-order MUSCL has a potential to improve spatial accuracy for all types of meshes by reducing numerical diffusion, most significantly for complex three-dimensional flows, and it is available for all transport equations. The MUSCL scheme is available in the pressure-based and density-based solvers. In this session, we reviewed different schemes for discretizing variables in Fluent. The same methods are also used for other variables such as energy, turbulent properties, radiation model properties, and species mass fractions. Moving forward, in the next session, we will solve examples using these methods to see how different pressure and velocity coupling schemes work. We'll also explore the relaxation factors and how Fluent utilizes them. Stay with us to continue learning and applying these concepts.